Hello, everyone, and let's start. So this presentation previously had a different name. It was called Basic Orchestration Concepts, and this is because it probably will give you some getting started information about container orchestration, but it should mostly ignite your learning search for how to orchestrate containers and how to develop applications for containers. So let's start with that. Just let me switch the slide. Okay. So the main question that I have for this presentation is, okay, I have containers. What is next? And you will see later in the talk that the thing that you have some containers, some Docker containers or some other Linux containers, it doesn't mean that it is very useful for you to actually run an application and be able to run it in production and scale, things like that. So let's look what we can do to answer that question. What's next after you have the containers? As Vivek said, and thank you very much, Vivek, my name is Vašek Pavlín. I work for Red Hat, and this is kind of who I am. I'm from Czech Republic. I like to travel, run, eat. A friend calls me hacker. It's not in a bad connotation, like I would be hacking some systems, but I'm more, when there is some problem, I try to solve it with some programming, and it's not always at best programming, it's just to solve the problem. So that's why he calls me a hacker. And I'm a proud Red Hatter. As you can see from my glasses, I wear them all the time. They have a Red Hat logo. And I met these guys from DigitalOcean at a conference in India, and it was great to meeting them. And when they asked me if I would want to present on their webinar, I was very excited about that. So I assume that some of you will know something about containers if you want to learn about container orchestration. I'm not sure if I can see the, sorry about the moving slides away and stuff like that. I'm not sure if I can see the poll anywhere, the results, because I wanted to know before I start talking about something, whether you know something about containers or not. So I'll assume that you know something, but let's recapitulate a bit. So what is a container? What is a Linux container? In a very general sense, it's a Linux process encapsulation, and it's also a very specific sense, because that's what container is. It's no magic. It's just you take a Linux process and you put some walls around it so that it doesn't see the world outside of the walls, and you can't really get into the walls from other containers. I would say that I always say in my presentations that there is nothing like container. The container doesn't exist. It's just a set of technologies that are put together in a way that we have something that we call a container. And the set of technologies were popularized by Docker Inc. And it was a couple of years ago, like 4 or maybe even 5 years, 4 years ago, let's say. And they basically took the world over with the containers, and everyone put at least at the beginning and even later, it's getting different now, but everyone put the word Docker in equality to container. If we think about containers in a broader sense, it's generally it's a good way how to package and distribute an application. Because if you look into the containers on how they are created and how they are distributed, it's basically just a tarball. It's some packaged content that you can move around, and there are tools to start and execute processes from that tarball, which then basically let you run some application, run some stack of applications inside some controlled environment. It's also a choice for many developers how to set up their development environment. And that's because it's very easy to create a container, run some process, test some changes, add some code, change some settings, and see what difference it makes. And if everything goes well, you can just ship it to some other colleagues or teams, or even to production, things like that. And it's starting to be a choice for many companies to how to run software in production. That makes sense, because if developers are using containers for development, why not to take the outcome of that and put it somehow into production? It might not be a straight path. You might need to change some things. You need to rebuild these containers, but still, it is a nice way how to get things into production and how to get them into production and into a real world in a standardized manner. And partially as a joke and partially as a very hard fact, containers and orchestration and everything around that is a cool technology now. It is a great hype, and if you want to get a great job, you might want to take a look at containers and think about how to be an expert in some part of that big environment, and you will probably get some nice opportunities. Okay, so let's assume you now know containers. So orchestration is next. I asked, what is next? Next thing is orchestration, because the thing is that if you have containers, it doesn't mean that you have a running application. It doesn't mean that it can scale it. You can run it in production. You need something to take care of the application, and that something is generally called orchestration. And there are many orchestrators, and I will talk about some of them, and I will talk about the concepts. That's why you are here, right? So I was at a meetup presenting about containers and orchestration and everything, and I had a discussion with a gentleman who asked something like, so I have this bunch of containers on my local machine, and I want to run them somewhere so that people can access them and they can do the work. And so I explained to him what is the container orchestration and how does it work today. And this is basically the drawing that I did on the whiteboard while I was explaining. So this basically can explain everything what is in the presentation in a very too long didn't read form. It might not be clear at the beginning, but maybe if you look at it at the end of the presentation, you might see some value in it. But honestly, let's start from beginning. So you now have your containers. I want to run them in orchestrated and production level manner. What do I do? So I'm sorry, I have to tell you that probably if you are not, if you don't know the stuff about cloud native and orchestrating things and architecting cloud native applications very well, you will probably want to or need to go back to drawing board. What does that mean is you will want to look at something called 12-factor applications. It was written, there is a website which was created by Adam Biggins. It came from Heroku, I think. He is a co-founder of Heroku. And they have written down 12 rules that if you keep them, you should be able to create a cloud-native orchestratable application. And I'm pretty sure, and I use that in my job and when I work with containers, that this can be applied to containers with very good success. There's another article. Well, the one is website. The second is just an article from Kelsey Hightower, who is, I think, evangelist of Kubernetes for Google, and he wrote something called 12 Fractured App. The difference between these two is that Kelsey admires the work of Heroku guys with 12-factor applications, but says that there are some pieces that are different for containers and that you should do things differently. So it's a very good read for you if you wanna really know. And Kelsey Hightower definitely knows what he does. So I picked a couple items from 12-factor applications and document. And those might not be the most important, but those were that I was fighting with originally, because I forgot to mention my background. So for the last half a year, I was helping my team to get on top of OpenShift, which is a container orchestration platform developed by Red Hat. It's based on Kubernetes. And I was helping my colleagues from various projects and teams to take their application that was not originally supposed to run in containers, to run it in containers, to get on top of OpenShift and run in a manner that we can scale it and support it for users. So first item for me, but not first in the 12-factor applications, is backing services. Imagine you have a database and you don't really, and you have some API, and the API is connecting to database and pulling some information, and the user is connecting to API and pulling the information from API. You should behave to the database. The backing services here says that you should behave to the database as if it was part of your application, or as if it was a microservice that you wrote to support your application. It doesn't matter that it's running in different cloud, in different the different companies providing the database. It doesn't matter if it's a different droplet or if it's running in a same on the same machine. You should just think about it from the point of API and from the point of contract between the database and your microservice, and how these things are connected, and not that it's something else that I shouldn't care about. Another point, number 6, is processes. And that's very important because, especially with containers, we care about processes. We think, well, people think that containers should run only one process, at least in some vague sense that if the process is forked 10,000 times, then it's still kind of one process. But in any case, if you run 2 microservices, each in a container, in a separate container, they will not be able to share memory. They will not be able to touch the same files on the disk. So what this point says is, make your processes share nothing. So they shouldn't share anything on the operating system level. They can share things through some cache and through some database and things like that, but they shouldn't share anything on the OS level. And the processes should be stateless, which means that if you kill the process, it's able to come up again without needing any information from the dead process. And I will come back to that later, because that's a very important thing with containers and orchestration. Another item is disposability. And that's also very important with containers, because what you should basically assume is that if you run a container in some orchestrator, it can disappear anytime. And that's not only for containers. If you think about any application running in any cloud, it can happen that a node, whether that's a virtual machine or a bare metal machine, will just go away because of some outage, because of some error. It can be hardware or software error, you never know. But there is a high probability that a node will go away. And your processes need to be able to recover from that. That if it's killed, and it goes well with the previous slide, and they should be stateless. So you should never think about that the process is around all the time. It can be killed, it can be stopped, started, restarted, anything. So think about it when you are designing your application. Point number 10, did I swap them? No, this was 9, this is 10. Development and prod parity. If you are developers, you might not care about the production environment. You would say that that's an ops problem, or that someone else should care about it, that it's, I don't know, SRE or service delivery or whatever you want to call it. But if you are anyone who cares about continuous deployment and continuous integration and continuous delivery, then you want to have your development and production environment as close as possible. And that's especially true for containers, because what we say is that containers are very portable. You can run it on your local machine, and you can run it in production without any changes, which works as long as your local machine and your production is very close to each other, which in most cases is not. So you should not assume it will work, but you should try to keep your development and production very close to each other. So these are the points from 12-factor applications. I didn't want to list all of them and read all of them. You are able to read it for yourself, and there are plenty of sources on the internet with user stories and success use cases of 12-factor apps and things like that. There are also discussions where they say 12-factor doesn't work and you shouldn't use it and you should use something else. So keep critical thinking and read the things and use what is good for you. As I said at the beginning, the presentation was originally called Basic Concepts in the orchestration, in the container orchestration. So now we are at the point where we understand that, I hope you understand that the idea of writing application for containers that should be run in some orchestrator means that you need to change your architecture. You need to rethink some things about your application. So now to make it even more clear, let me talk about the concepts that you can find in your in any container orchestration that you can use, and that's Kubernetes, OpenShift, Mesos, Docker Swarm, kind of Docker Compose, but it doesn't really scale. It's just for local development, but it takes some of these, and there are many more. Is I don't know, Roku, and there's many more, Rancher, but they share the same concepts. So let me start. Scaling. If you run something in production for users, you will want your application to be able to scale. Let's call it traditional or mode 1 scaling, maybe, is getting bigger. If you have a database, a big SQL database, doesn't matter who provided it, and you want to scale it, your first thought probably will be, I will request a bigger droplet in DigitalOcean, and I will run my my database on a bigger droplet. And that is okay for databases, for example, but if you have a small API that you want it to accept many requests, it might be more beneficial to run it many times instead of one time, but on a big machine. And that's the difference between vertical and horizontal scaling. So vertical means that you take something and you make it bigger. Horizontal means that you take something small, ideally small, and you make more copies of it. So that's great because it solves the high availability problem as well. If you have a cluster that has multiple nodes, and the nodes are scattered across multiple availability zones, for example, you can then run your API on multiple, or your containers on multiple availability zones, and if one goes down, you still have some load balanced way of running users into your application. So that's scaling. So for containers, we want horizontal scaling. So we want our containers small. Another very important thing, and it's not just for containers, it can work for VMs as well. As you may have noticed, this talk, you can apply it not only to containers, but you can also apply it to generally cloud-native development. And I specifically put containers in the name because that's how I learned about all these things. But you can apply it anywhere else. So immutability, what does it mean? Imagine you have a machine. Let's say it's a bare metal machine, and there is some application running on it. And what you need to do is that when you start a machine or restart a machine, you need to manually tweak some things inside the machine, inside the operating system, to make everything started, and maybe reconfigure something and things like that. This is great, but that means that your application, that your infrastructure is immutable, which means that it's open to you, that you can go inside and you can change things. What we want to achieve with containers is immutable infrastructure or immutable applications. So once you have a code and you build your container from the code, you never touch what is inside, apart from configuring the container with either mounting a file in or using environment variables, but you never change what is inside the container, so that if there's something bad happens, you are sure that this is the container that was run, this is the container image that was started, that was distributed, and that you can go and debug the issue without thinking whether your administrator or someone got inside and changed something. So think immutable when you develop containers. Everything has to build on the build time, apart from some configuration of like URLs and secrets and things like that. With immutability, there goes another concept, and that's traceability. Traceability is very important, and you can also call it auditability, or maybe some other words. And what does it mean is that you are a developer, you write code, you push the code to Git. There is some webhook, ideally, so it's automated, that says, hey, there is a new code, build an image for me. When the image is built, it goes to registry. And when it's in registry, some orchestrator can take it and run it. This is great. But if you are not able to trace what is in the cloud, in your cluster, in your orchestrator, back to the commit that the developer created, then you have no way how to know what broke your application. So for code, it's easy. If you commit something, there is a commit hash. If you build something, there is probably a build ID. If you build an image, there will be some image hash. And when you push it to registry, you can give it a tag, which is like a name for the version of the image or something. And then it goes to the orchestrator. And what I prefer to do is everything here should carry the commit hash. So when I deploy some image, it will have the commit hash as a tag, as a name of the image, basically, well, a part of the name of the image. So that if I see a failure in my orchestrator, I can go and say, hey, you committed this to the Git, and it contains some error or some mistake or bug or something, because it doesn't run in our orchestrator. So make sure that you are able to trace anything back to your code. Okay. So next thing is composability, and that's a pretty obvious thing, but people do not always think about it at first. If you have an application that should be run in a cloud, in orchestrator somewhere for users, and you have maybe multiple components of the application, you will want to be able to connect to those components and connect them together. So when you are designing your application, you need to think about how it will be run and what are the interfaces that it can expose. Because if you are running on a single machine with just processes, they can communicate in multitude of ways. So they can share memory, they can use the same files on the disk, they can use pipes, they can use Unix sockets, things like that, which when you close your application into container might not be true. It might not be true. It might be needed that it exposes some REST API, or it exposes some socket outside of the thing, or it talks to database, writes some data in, and some other component takes them out, or there is a message queue or something. So think about how you can force composability into your components, and it basically means that you have to define very well your APIs, and you need to document them. And it's very, very important with containers, because if someone gets only the container, he needs to be able to trace the documentation back and see what is the API of the container. Otherwise, he will have to find the code, he will have to get inside the container and try to do some things manually, and that's not a nice thing to do. I'm back at stateless. So another concept for me is statelessness. And what does it mean is that if you have an application, I've already explained that, but bear with me. If you have an application that is running in a VM, for example, and you wanna keep some state. So I wrote a lot of PHP applications when I was at school, and I always kept the state inside on the server inside the application based on some session ID provided by user. So if the server went down, the state was lost, right? So with containers, you have to assume that the containers will fail and that they will go away. Because, for example, let's say you have a cluster of 100 machines and you want to do upgrade, things will get restarted, things will get moved from one machine to another, and there might be failures, like 10 nodes will fail the upgrade and you will have to replace them with new nodes or something. If there is state inside your container and the container gets moved, it gets moved only in a way that there is an image that is started somewhere else and it gets the same configuration, but it doesn't get any content of the original container. So you always have to think about where to put the state so that it's outside of the container. It can be, again, database. It can be a mounted volume. It can be anything else. We are in the cloud world, so we can use, I don't know, various databases, various caches, key value stores, whatever. But always think about the state of the container. If there is anything you need to keep for the user, keep it somewhere else than inside the container. One, and I think this is the last concept that I have, and that's, and for me it's very interesting, because when I was preparing this, when I was preparing this presentation, I realized that this is very important and it goes well with all the above, but people don't think about it this way. So if you have your machine that is nicely tweaked, it is optimized, it runs some application that is critical for you, and you get a ping at, I don't know, 2 a.m. in the night that the machine is down. You will go and you will try to fix it and bring it back up. So either run the application again or try to reboot the machine or something. And then the application or the machine application is resurrected. It is still the same thing, the same machine, the same application, the same data inside that machine, and it's resurrection from the meaning of the word. But with containers, we want to think reincarnation. So if something dies, it stays dead. It never goes back up. It never resurrects itself. It always reincarnates on some other node, on the same node, maybe from a same source, with same connections, but on a different place with different context. So resurrection, reincarnation, very important. I don't know how many of you heard about serverless or function as a service. It is a very popular topic these days. And basically, I started to dig into it with a friend, and what I came to the conclusion is that containers are not that different. Anything you can do with function as a service, you can do with containers with some more work. But anytime you develop application for containers, always think serverless. So whatever is a rule to develop serverless application, like make your function small, try to not run too much stuff, make your dependency small, things like that. It's very same. The container can go down anytime. It will be restarted. The state is not there. Things like that. So think serverless when you architect something for containers. I will talk a bit about OpenShift. So this is like, you now know the concepts of the container orchestration. And you should be able, when you start a new application or you go back to the drawing board, you should be able to think about, okay, so what do I need to do differently to make my application container ready? I would like to say something more about one orchestrator that I personally use at work, and if I want to try something with containers, excuse me, I do it with this one. It's called OpenShift. It's open source. You can find it on GitHub. You can run it very simply. I will show you in a minute a droplet that I created on DigitalOcean, and I basically set up an OpenShift instance there in like 10 minutes. And you can try it out. You can run some applications. If you want to do a proper kind of a production-ready deployment, there is Ansible scripts or Ansible playbooks, sorry, which you can use, and you can try out. From what I heard, they should work anywhere, so on DigitalOcean as well. You just need to specify your nodes. It will not create them. It will not create them automatically, but it's also open source. So if you want to contribute, I think that guys from OpenShift will be happy. So what is OpenShift? It is a Red Hat Kubernetes distribution, which means that we take Kubernetes, we add some features, and we call it OpenShift because it's all open source, and we contribute everything what is possible and what Kubernetes upstream wants to accept. We contribute it back to Kubernetes. So things like ingress in Kubernetes was originally routes. In OpenShift, there's many volume plugins, the storage plugins that were contributed, out of bug fixes, stuff like that. So there is a link here that you can go to and try it out. I'll show you in a minute. Okay, so if you take this orchestrator, OpenShift or Kubernetes, it applies to both. How is it done that it can run a container with all the concepts that I mentioned, with scalability and traceability and kind of audibility and that things fail, but fail fast so that you don't even notice that they fail? I mean, if container dies or something, how is it done? The main concept in Kubernetes and OpenShift is desired state. What does it mean? Imagine you have a nice picture. I took Mona Lisa here, and this is what you created, and you said, okay, this is my application. It consists of these components, it has some routes, it has some connections, some services, things like that, and this is how it should look like. Please, OpenShift or Kubernetes, run it for me. And then the orchestrator goes and then tries to recreate what you gave it in a real world. So it actually tries to run the containers, set up the routes, set up the connections, fulfill the requirements that you gave it. So if there is a requirement for 2,500 gigabytes of memory, it will try to find a node in the cluster with 2,500 gigabytes of memory. It will try to achieve the desired state. Another thing or part of the things, how it's done, is that there is plenty of abstractions. So if you run your orchestrator, like Kubernetes or OpenShift, there will be a network, overlay network. So it will take the network of the nodes, it will create another networking layer over that. It will take a container, and then you will create an abstraction over the container, which is called pod, and I will talk about it more. So it's full of abstractions, and that's how it can manage all the things and then make all the connections and keep the thing running. It's using, so in technical detail, Kubernetes and OpenShift are using etcd at its bottom, at its low-level part, and the etcd is a key value stored by Chorus. And basically what you define, and I will show you some of the definitions, what you define will basically be defined in the etcd and distributed across all the nodes, and the nodes will talk about or exchange messages like who starts what and what is the way how to start it and things like that. So these are the abstractions inside the OpenShift and Kubernetes. Container we talked about, that's pretty clear, right? It's at this moment it's a normal Docker container that you can build on your local machine, but then the abstractions kicks in. So you take that container and you wrap it in some YAML or JSON file, and the basic one is pod. Pod is a minimal unit that you can control inside Kubernetes and OpenShift, and that's basically what runs your container. And you can put multiple containers inside one pod. Think stuff like sidecars. So you have a container and you have some logging agent that pulls some logs from that one container and pushes them to some log aggregator. So that's why you might want to have multiple containers inside one pod. Then on top of pod has its IP address. But because you can scale, so you can run multiple pods of the same instance, you need something that will load balance between them, and that's called service. And if you take a Docker Swarm orchestrator, it has very similar concepts. It goes directly from service to container. It doesn't have pod, but the concepts are very similar. So the service is basically an internal load balancer to the orchestrator. So if there is any traffic coming and it should go to pods and they are scaled, so we have like 10 of them, the service will make sure that it's load balanced across all of them, and it exposes a single IP address for the outside world. Well, not for the outside world, for the world inside the cluster. If you want to expose something to the outside world, you will use route, or in Kubernetes, ingress. And the route is basically DNS. So you give it some name, it will create some nice URL for you, and you can route through that to the service, and from the service it goes to the pod, to the container, and your application can respond, right? So if you think about it from the perspective of what you know from, for example, DigitalOcean, you have a droplet, and that's a pod. It runs multiple processes, which are like containers. You have some load balancer, which is a service, and then you have some DNS setup, which is a route. And as I said, service will cover all the instances of a single pod. So if you scale from 1 to 2, it will look like this. So we have 2 pods and 1 service that will route to those pods. Let me now switch over to my OpenShift console. I will try to make it a bit bigger, but I'm not really used to MacBooks. So I will do it by clicking. So this is hope you can see it. This is how OpenShift looks like. This is running in a DigitalOcean droplet. I can show you here. This is my droplet. It's based on Fedora Atomic 64-bit. Atomic is a special edition of Fedora that we release for containers. It's optimized for containers, very minimal, and it can run containers easily. It has pre-installed all the stuff like Docker. So I just basically downloaded OpenShift and ran it with the OC cluster app command, and I got this. And what I just talked about is basically here. You have pods, you have services, you have routes. And I imported an application. It's an example application, I think, from some Docker birthday that we took and tweaked it so that it runs in OpenShift with my friends. And this is basically what you can see. There's many pods, and some of them are from the builds, because OpenShift can do container builds for you. And some of them are actually running applications. So if I click on it, I should be able to see that there is a container inside. Sorry, here, container inside that's coming from some image. It was built. There is even a connection to GitHub, so I can see like what commit and by whom it was authored in the container. So it's pretty powerful system. And I can even take a look at logs for that container. So this is what it printed out. Socket ended. I have no idea what it means. So maybe things will fail. And I can even go to terminal, and I can kind of SSH from the browser to the container and look what is inside and do things. So this is kind of against the immutable concept that I told you, but it is great for debugging. Another thing that I mentioned is services. So we see that I have a couple services. Some of them are exposed to routes. These two actually are exposed. These 3 are only internal. And if I click on one of those, okay, let me pick another one. So if I click on one of those, you can see that it has some IP address and host name, and that it's connected to some pods. So if I would scale the pod, I can show you later, it will show multiple of them. And then it's where the traffic comes from. Where the traffic comes from is the routes that are defined. Just to show you, the application looks like this, and the architecture of the application is that there is this voting at front end. So then there is this voting result front end, And then there is two databases, Redis and Postgres. And Redis is like a cache for the votes, and then there's a worker that processes them and puts them in the database in the Postgres. So I'm now 50-50 because I didn't vote yet, but I will vote for OpenShift. I'll click to results, and nothing will happen because I broke it somehow. So let me try to, yeah. So see, that's what happens when you play around with. I did some changes, some late changes. So let me try one thing, and that will be redeploy the result. What is happening now is that I basically take, you can see that these were triggered by image change. So there was a new image built, and this one was triggered by me. And it basically means take the deployment, the description, and make the desired state again. Renew the thing. So now it's connected to database. It wasn't before, and you can see that it's changing, and it reacts. I can show you one more thing. Okay, I still have 50 minutes, so very quickly, let me go to the pod. I was talking about that YAML or JSON that you can see and use. So this is it. It looks a bit more complicated here than it looks when you write it, because there is things like status that is automatically generated, and it actually is status from OpenShift. But the main part is basically here, where you set up environment variables that you need for connecting to database. There's some secrets. There's the image that is built, and then I want to run from liveness probes. I will talk about it a bit more later, and many other things. So I definitely recommend playing around with OpenShift, because it is a great project, and it will give you a lot of headache, but it's worth it. So back to presentation. I have some best practices. They are for OpenShift. As I mentioned, I'm working with OpenShift daily, so they will apply to other things as well, but they are mainly for OpenShift. So I've already described this, but if you are creating images, think Docker build something with tag my image latest, right? Never use latest if you want to use that image somewhere else than on your machine. Because if you do that, then you will never know what you are actually running. You can use some things like labels and I don't know what else, some metadata information, but it's not obvious. And if you want to run something very quickly and you want to debug something very quickly, you want to use versions. So I do use semantic versioning if you have your application if your application is releasing, or use commit hash if you are doing proper continuous integration and continuous deployment. If you don't know anything about OpenShift and Kubernetes, this might be confusing, but if you know something about, and you will learn something about it, you can configure your containers through environment variables or secrets and config maps. Let me just quickly show you here. You could already notice, but it was pretty quick, so let's do it again. Here, when I set the environment variables, which is some name, I go and say value from secret and some key and name of the secret. And that's exactly what I'm talking about. If you just put the value in there, it's very hard to trace it. It's very hard to maintain it. So use the secrets. And why is that? Is on the next slide. Basically, it's because of portability, but it's because you probably will have multiple environments. Like we do have production preview and production and bunch of testing environments. So if you want to move between these two and you want to deploy one thing to multiple environments, you want to have your deployment configuration, the big YAML that deploys everything, you want to have it separate from these configuration options. So if you use secrets and config maps, you will be able to do it because you will be able to keep the sets of secrets and config maps separately. And I mentioned route here. That's the DNS thing for containers for OpenShift, and that's because if you have certificates in there, to make your route to use SSL and TLS. You will want to keep your routes for every production or every environment separately as well. I think it's the last thing. Always use health checks. There is a bunch of health checks in OpenShift, liveness probe and readiness probe, and maybe something else. I'm not sure. But these two are very important. Readiness probe tells when your container is ready, so you can say deployment was successful. Liveness probe is, do I need to redeploy? Do I need to restart the container? Do I need to do something about it? Do I need to report the error? So that's for liveness probe. If you have an application, like I have an API that is using database, which I already mentioned, make sure that your health check will actually, the code for the health check, like some /API/status, will actually test whether the database is available. Otherwise, you are just testing that your API container is started, but if your database is not available, then it's very hard to tell whether the API is useful or not, right? If you ever use OpenShift, always use OC apply to upload your YAML configs, because OC create breaks things when you then change some values. Cannot be changed if you use OC create and don't use OC apply, so always use OC apply. This is, I think, the last thing. So don't use Java in containers. No, I'm just kidding. Sorry about that. If you like Java, obviously you can use Java, but always, and this doesn't only apply to Java, that applies to anything, always set some resource limits, because it's very easy to exhaust your cluster or node in the cluster without setting resource limits. And the problem is that with Java, with OpenJDK up to JDK 8 something, Java didn't really care about the resource limits set by OpenShift or by the containers, by Docker. So it would consume anything, even if you would tell it not to, or you'd restrict the container. After some update from OpenJDK 8 something, I really don't remember, it actually takes in account the limits that you put into container, and it will actually keep the JVM according to those limits. There is much more concepts, there is much more best practices, and there is much more to talk about with OpenShift and Kubernetes and containers and Docker and architecture of applications.